Welcome back. Now I'll be going into 9.3, which is the air standard assumptions. So the air standard assumption has to be made before we even go deeper into this chapter, because without the assumptions it's very difficult for us to solve the questions. So the first thing is the working fluid is air. Okay, the working fluid is air which continually circulates in the closed loop and always behave as an ideal gas. Of course, real case scenario, it's not only air. It's got a lot of other gases inside. We also have either diesel or petrol inside, unburned diesel or unburned petrol, soot, a lot of other things that's in the air itself. But then now, in order for this study, we are just going to say that it's purely air that is circulating in the loop, right? The next one is all the processes that make up the cycle are internally reversible. So it's a perfect process. There's nothing that is no friction, no heat loss, nothing. It's just so perfect. Yeah, that is another assumption that we need to make. The next one will be the combustion process is replaced by heat addition. You see, in a cycle, I'll just show you one example here. Okay, this is your petrol, what do you call, piston. Okay, the combustion is actually happening inside, but then in the assumption we always say that the combustion is actually not happening inside, as if the heat is actually coming from somewhere else. It's a bit tricky, but this is how it is. So when they draw the cycle, they will draw equipments. Actually, the combustion is actually happening within this equipment. It's happening here. But for the easy understanding, it actually comes from, they assume that it's actually coming from outside. So that is for heat addition. If heat rejection, it's actually coming from here and going out. But in real case scenario, it's actually happening within the equipment itself. But they just say that it is actually going out. Okay. So it's a bit tricky, but this is how it is. So you need to actually understand it that way. Okay. Next would be the cold air standard assumption. So the working fluid is considered to be air, at constant temperature of 25 degrees C. Real life, of course, it's not 25 degrees C, it's much higher. Okay. Next would be air standard cycle. The cycle for air standard assumptions are applicable. Okay. Now, let's move on to 9.4, which is the reciprocating engines. An overview of reciprocating engines. So there are certain terms that need to be explained here, okay, which you need to understand the terms. It's very, very important, because we're going to look at two types of engines here. One is diesel and another one is Otto cycle, or another word is your petrol cycle. Okay, just pay attention. The first term would be TDC, which is the top dead center. Okay, so top dead center is the position of the piston when it forms the smallest volume in the cylinder. So which means if the piston, you know what's a piston, right? This piece here, this whole thing is here, is a piston. So when the piston moves up, this is called the top dead center. When the piston moves down, this whole area is called the bottom dead center. Okay, the diameter of the piston, the diameter is known as the bore. Okay, so this is the intake valve and this is the exhaust valve. So when there's finished combustion, this will go out this way, and intake valve, one second, sorry. The intake valve will allow the petrol and air to come into the piston itself. Okay. And then we have the minimum volume formed in the cylinder is when the piston is at the top dead center. Or another word to call this is actually the clearance volume. Clearance volume. Okay, so the volume displaced by the piston as it moves between the top dead center and bottom dead center is called the displacement volume. The displacement volume. So this is called the displacement volume. Okay, the ratio of the maximum volume formed in the cylinder to the minimum. It means V max divided by V min is given by the compression ratio R. Yeah, so that is the compression ratio R. Now, what is the mean effective pressure? MEP. MEP is work net divided by the difference between the volume, which is the displacement volume. Okay, so these are the terms that you need to understand. And then we have got two types of reciprocating engines. Yeah, one is the spark ignition engine and another one the compression ignition engine. Okay, in layman's language, what is the spark ignition? This is the petrol. Yeah, petrol engine, or we call it the auto, auto. Whereas this one is the diesel engine. So we're going to go into both. Yeah, we're going to go into both. Yeah, both are within our syllabus. Okay, so the first thing is the auto cycle. Okay, auto cycle. Okay, now if you look at this auto cycle, I'm also going to attach some other files, video files, yeah, which is from YouTube. Yeah, I'll just post the link to you that you can just go through the auto cycle and the diesel cycle. Yeah, okay, so that is for your better understanding. Yeah, okay, now this one, this is what is actually happening in your engine. Yeah, got a nice beautiful one this here. Okay, look at this. This is the actual thing that is happening in your engine. Okay, but of course it's very difficult. Look at these. There is no end of combustion. There is no sharp points here, like what I've explained to you. It goes in and confuses, you know, very difficult to study. So this is what we have idealized, and this is what that is easy to study. So this is known as the ideal cycle. Yeah, ideal auto cycle. Okay, now you remember the assumptions that we have made just now, the 4 assumptions that we made just now. Yeah, okay, let's look at it, what's happening in a compression stroke. This is the actual 4-stroke spark ignition. So in your actual stroke, what's happening? This thing is actually moving up. Okay, compresses the air inside here and fuel. Okay, and then we have the, once the thing is compressed, we have the spark plug releasing the spark. So when it releases the spark, okay, what happens? It will expand. Okay, there will be a small explosion. So this will be forced pushed down. So once it's forced pushed down, you have to remove the exhaust, right? Yeah, because it's moved down. So this will start moving up, and the exhaust gas valve will open. Then this combusted air, combusted petrol, and all this thing will move out from the exhaust valve. Yeah, and then we have the new intake again, which is the air and fuel mixture coming in, and the cycle goes. It starts and it will just carry on going and comes back and goes on. Yeah, but for better understanding, in our syllabus itself, like what I've told you, yeah, they have idealized. So when you idealize, can see 1, 2, the very sharp points. You definitely know what is happening at where. Yeah, so this is an ideal auto cycle. It's actually this cycle, but we have just simplify it for you. Yeah, so the first case would be isentropic compression. So what is isentropic? Your S is constant. Yeah, compression. When you compress, pressure will 1 to 2. Pressure will start increasing 1 to 2. Okay, 1 to 2 compression. And then remember what I told you about the Q, the heat that's coming in, as if it's coming from outside somewhere, but it's actually same. The scenario is actually happening within the piston. But always, yeah, for an ideal case, we always say that it's coming from outside. So look at this, 2 to 3, it's coming from outside. Yeah, what's happening here? It's heat addition. Okay, once heat added, what happens? There will be an isentropic expansion. The pressure will drop. Pressure 3 to pressure 4, yeah, it will drop. Yeah, because you have the increase in volume, because it's an expansion. Okay, once it's done, then it goes from 4 to 1. So 4 to 1 is constant volume, where the Q actually goes out. That's the bottom dead center. Yeah, so this is the whole process. So what you need to understand is this the Otto cycle, because the questions, they will always ask you to calculate 1 to 2, 2 to 3, like a jigsaw puzzle, 3 to 4, yeah, continuously. Okay, so let's move on to solving one of the example, yeah, in the what do you call, in the textbook. But before that, I'll just want to introduce you to a formula. It's page 494. It's the question. Let's look at a formula, page 494. Okay, and this is kind of like a useful formula. Okay, look at this. Q in. Can you see this? Q in. U3 minus U2 equals to CV T3 minus T2. So you need to understand. So this is a standard formula for Q in, and then this is a standard formula for Q out. Can you see? That's Q out. It's happening between 4 to 1. Okay. And what is the efficiency of Otto cycle? W work net divided by Q in. Or in another simple word, you can actually take 1 minus T4 minus T1, T3 minus T2. These are favorite questions that they usually will ask you. Yeah, and this is the compression ratio, V max over V min, commonly 1.4 for petrol engine. Yeah, for petrol engine is mostly 1.4. Okay, so with that, let's move on to solving a question. Yeah, okay. Before we go into solving the question, there is a slide on the summary of the formulas. Yeah, similar to the textbook. Can you see this? Yeah, these are all summary. So mostly these are the formulas that you need to use in solving the question. So now we will just move on to the question itself. Yeah, we are done with the PowerPoint slide, because the coverage of this video would be up to 9.5, yeah, which is Otto cycle. So let's just move on to answering the question. Yeah, I'm looking at example 9.2 from the textbook, page 496. Yeah, so an ideal Otto cycle has a compression ratio of 8. So the R value is 8. At the beginning of the compression, air is at 100 kilopascal, 17 degrees C, and 800 kilojoule of heat is transferred to air during the constant volume heat addition process. So just read all this question, jot down the important points, and then you need to actually find for the initial values. Yeah, initial values. We'll come to that shortly. Yeah, and just pay attention here. Accounting for the variation of the heat addition air temperature, determine. Okay, this is how they always ask. A, the maximum temperature and pressure that occurs during the cycle. B, the net work output. C, the thermal efficiency. D, the mean effective pressure of the cycle. So these are actually very standard question. Yeah, A, B, C, D. Okay, we can totally ignore the last question. Okay, we can totally ignore the E, because that's not the favorite question. A, B, C, D will be the coverage of your syllabus. Yeah, so an ideal cycle is considered. An ideal Otto cycle is considered. So these are the solution assumptions that you need to make. The maximum temperature and pressure, the net output, and the thermal efficiency mean is to be determined. So the first thing is the air standard assumptions are applicable. And then we have the kinetic and the potential energy changes are negligible. And then we have the variation of specific heat with the temperature is to be accounted for. Now, looking at the PV diagram of the Otto cycle is described, is shown in figure 9.19. Okay, I'm just going to snipe that figure. Okay, the diagram, yeah, the diagram that is mentioned in the question. Okay, diagram 9.19. So this is the diagram. Yeah, so this is how an Otto cycle will be. So these are the hints. Yeah, these are the hints where V1 is equals to V4, V2 will be equal to V3, which is actually 1 over 8 of V1 that is given in the question, right? Okay, just now we saw the question. It is 8 times. Can you see? The compression ratio is 8 times. Yeah? Okay, and then what we have here? Okay, and then what we have here? We have to find 1, 2, 3. So 2 to 3 is same volume. 3 to 4 is same isentropic. So the S value here will be the same. So these are the hints that you can use for the solving the question. Okay, now let's get back. What are they asking? A maximum temperature and pressure occurring during the cycle. So all the values that you have here, the beginning of the compression ratio, pressure is 100 kPa and 17 degrees C. So you have to write this down. So we have the T1, which is just now. T1 was because it's all not in one page. 17 degrees. So 17 degrees is 290 Kelvin. So what you need to do, you need to go to the steam table, table A17, okay, and look up for the U1 and VR1. Remember, this is VR1. Yeah, it's a bit different from the the normal V. Yeah, okay. So the table A17 is a bit unique. Yeah, so we have T is ideal gas property for air. We have the temperature. We have H, and then we have PR, and then we have VR, and also U. So the VR value, once we have the VR value, so keep it aside. So we know process 1 to 2 is isentropic. Remember what I told you? The same line. Yeah, 1 to 2 is isentropic. So isentropic means the entropy is the same, right? The entropy is the same. Okay. So with that also we can actually compare the ratio, because we know that VR2 over VR1 is actually equivalent to V2 over V1, which is 1 over R. And what is the R value? It is 8. It's given in the question. So when we have the VR1, can you find the VR2? So with the VR2, you can actually go back to the same table. You can find for temperature 2 and U2. Yeah. So the next one is also to find the pressure. So to find the pressure, you can compare using your ideal gas law. Yeah, PV over T equals to PV over T. So all these values you have, yeah, just have to plug in and you can get the pressure. So that would be for you have the maximum temperature and pressure that occurring at the end of at state 3. Okay, so this question is not complete yet because you have got 1 to 2. Next is you're going to move 2 to 3. Okay, now in process 2 to 3, you know Q in is happening. Yeah, let's look at this. 2 to 3, Q in is happening. It means there is a heat addition process. So what is the formula for heat addition process? U3 minus U2. Remember the slide that I showed you earlier? Yeah. So you just have to look for the value of U3. U3 you don't have the value, but the question has given you the 800. How much heat is coming in? You know your U2, and then you minus, you get your U3. So with the U3, you go back to the steam table, yeah, and then the same table A17, yeah, you can get your T3 and your VR3. Okay, that's how you do. It's like a jigsaw puzzle, one after one. Okay, so with that also, once again, you can compare your PV over T, PV over T, and then you can get the new pressure. Now look, V2 over V3. Why the value is 1? Because it's the same. Yeah, the volume is constant. Can you see? 2 to 3, the volume is actually constant. So that's the reason why V2 over V3 would be 1. Yeah. Okay, so you have got your pressure. So this is actually answering the question. The highest pressure and the highest temperature is at point number 3. Yeah, point number 3. So you have to find the P3 and the T3. So you have done that. Yeah, you have found the T3 and you have found the P3. So you have settled the first part of the question. The second part of the question is actually asking how much of work output of the cycle is determined either by finding the boundary work or by integration and adding them, or finding the net transfer. So there are few steps in it. So we will just look for the easiest step. So the easiest step is actually using your W net, which is equivalent to Q net, because this is a cycle. Q in minus Q out. Q in is given in the question 800. Yeah, it's given in the question. So what we need to find is Q out. So let's look at how to find the Q out. Okay. So now where is the Q out? The Q out is actually happening between 4 to 1. Okay. So you got all this information. You got your 2, the 0.2's pressure temperature. You got your 0.3's pressure temperature. Yeah. Now you have to find the fourth one. Okay. Let's look at that. Okay. Now you're comparing. When you compare, yeah, you know the ratio is 8. Okay, so you have the value for VR3, so you just have to multiply you get 48.3. Go back to table A17, you can get your T4 and your U4. Okay, remember from the slide that I've showed you, the slide that I told you, the list of formulas which are important. So if you see here, Q out is actually U4 minus U1. Okay, going back to the question, minus, yeah, minus means the other way around. So U1 minus U4. If U1 positive, then you take U4 minus U1. Okay, so so you have the U4 from the previous one, 588, and U1 was from the previous calculation that we have found, it's 381. So which means Q out is actually 381. So with that, you can find the work net. Yeah, so this is a simpler way. And the next question is actually to find the thermal efficiency. So what is thermal efficiency? Work net over Q in, which is in this case 52.3. Yeah, 52.3. And they are also asking you on the what do you call efficiency of the auto. So efficiency of auto, there is a standard formula that you need to just plug in all the values inside. You can get it is 56.5. And the last part of the question is actually to find the MEP. MEP also has a standard formula. You just have to plug in all the values and you can find the MEP. Yeah, so if you see this first part of the A, yeah, the part A is something that you need to practice over and over again, because it's like finding for missing values, missing jigsaw puzzle. If you have this information here, you can compare and find the information here. When you get all the information here, then you go to point number 3, and then you find for point number 4. So it's like a cycle, it's like a jigsaw puzzle. Yeah, so that is this important part. And this example that I've just explained to you is really, really very important. So please pay attention, yeah, and take this as serious. Yeah, I'll see you again in the next video.